Hey everybody, so I have another unique video for you today. In this particular video, I have created the world's first implementation of a graph neural network being trained via reinforcement learning. And so I've created a graph neural network and a CNN in this instance, or a convolutional neural network. A convolutional neural network is visual, and then I've created this QBER environment, and then I've created a graphical interface of this QBER environment, and created a this environment into a graph, and then through my AI geometry that I created, kind of mapped the nodes, the edges, and the clusters of this environment into geometry, and then I'm feeding that to the CNN, and then the CNN is operating off of that data and then training off of it. And then also the model also is incorporating energy in the model. So this model loses energy. It loses a lot of energy anytime that it jumps off. So it actively avoids jumping off. And then it loses a little bit of energy every time that it jumps on a yellow square as opposed to a blue square. And then it gains energy every time that it jumps onto a blue square. And that energy is on top of its reward structure. So it's called reward shaping, where I utilize more than just like one trigger to shape the reward structure, and adding more and more levers to be able to pull. I get the concept from MOBA video games, where they utilize that kind of concept within their characters when they try to balance them via multiple levers. The more levers that they have on the individual character, the more balanceable the character is. And then so that's what I try to do in this instance. This model is training and it's moving via three different inputs. The CNN layer is getting the visual of exactly what's going on. The GNN, the graph neural network, is graphing out and making calculations. And then the energy is calculating the entropy and then trying to maximize the amount of energy loss or minimize the amount of energy loss of the agent. And then so all these things combine, and then it provides what we're looking at here. With this model overall, I've trained a lot of these QBER models now via reinforcement learning, and this model does score very well. I've been watching this model for a while. It's not been doing so good since I started this video, but it'll clock into in the range of a scores of around 1,000 or so. And then it's been running for about a half an hour. Yeah, so the score of 1,000 is like very atypical for these type of models. So I would say that this model is learning very efficiently for what it is. And then because this is such a novel implementation of this, I decided to make this into a GitHub repository as opposed to sharing it via Colab or anything along those lines. So the GitHub name for this is called NeuroGraphRL. And NeuroGraphRL is a novel reinforcement learning framework that integrates graph neural networks, convolutional neural networks, and energy conserving strategies to train AI agents on complex environments, such as Atari games. The framework leverages the power of graph-based processing and visual feature extraction to create smarter and more efficient agents that understand both the spatial and structural element of their environment. And that's the goal here, right? Is to understand both the spatial and structural elements of the environment. That's why I'm utilizing the CNN. That's why I'm coupling it with the GNN and giving it all of that data, right? And then let's take a look at what the code is here, just giving you kind of a brief rundown on that. So essentially, we have our replay structure, and this is pretty typical for reinforcement learning. So it's the model doesn't get the information in real time. It gets it in batches of 4 frames. So every 4 frames, the model gets the data, and then it's processing the data off of that. And then it's in black and white, and then a bunch of like resizing and reshaping. So it's not actually seeing the same thing that we're seeing, but then just reshaping that. And then we put it into, I have this graph attention layer. So its attention layer is actually graph-based. And then I have this graph processing stream, so it can process that data, right? So it takes in all of this graph data, and then the graph processing stream is what feeds it to the model, and then this is what the model takes in from that. And then the next class that we have is this energy conserving neural network. So the energy conserving neural network is another layer within the model, which is essentially responsible for the energy conservation, and then its job is to essentially recognize that it has energy, and then by default, by just doing that, by not programming anything else, by the laws of conservation of energy, it starts conserving energy. So very straightforward there. And then feeds all of that. That data then gets passed back into that graph processing stream again. And then so making sure that all of this data is getting fed back to the model, essentially. And then we have our feed forward loop so that all of this data gets processed through the model. And then we have, this is like the environment that the model gets fed, right? So it's called Kubert graph in this instance. And then this is just the graph of the environment, the number of levels, the node mapping. And then again, this is all mapping to nodes, right? So essentially, if you're familiar with GNNs, I take the geometry and then I've invented, again, it's called AI geometry is what I call it, where essentially I can shape certain concepts into nodes, edges, and clusters is what I shape them into, and then it's kind of formalized. And then so in this instance, I'm shaping the environment into the nodes and into the edges, and then feeding that data into the model so it can understand it. And then we have our training mechanism and our training environment that goes here. I'm using standard Atom optimizer. So I'm utilizing like very standard optimization, just Atom, I don't know what else to pick. And then ReLU optimization. So like this could be heavily adjusted, right? I'm just like, I just picked the most basic things ever. I give it an epsilon decay, the most basic epsilon decay ever of 0.01. So again, like I went like highlighting here, I went with like default settings, basically is what I'm trying to highlight within this. There's a lot of play to improve this model's performance, but this model's performance is outperforming other models that I have tested within this range. Highlighting what would be the drawbacks of this model, right? It's important to highlight that. This model is very computationally intensive compared to other models. It's like, if you've noticed, as this Kubert game is running, this Kubert game is running slowly, and it's running a lot slower than it would in a typical game. It's processing a lot of information throughout and like before it takes in each individual action, right? So what would be the drawbacks of this system? It's slow, like it's taking a lot of resources, and I wish it was a lot faster in that instance, right? It's going to take like 6 hours total for this model to go through and train, whereas like if it was actually like speeding up and I could actually utilize like multi-processing, things like that, it could be like half an hour. So it's really slow, and you can see the movements are slow even with the way that it goes through, and that's just how it is. But other than that, there's no drawbacks to this model that I've seen. It's awesome. So I'll leave a link to this GitHub and a repository, and if you like this type of content, please like and subscribe. Thank you very much.